a.m. Eastern time. So I think that we were getting started. Yeah, because to keep everybody on the schedule. I'm sure there are some people will be joining a little bit late. Good morning from Detroit. You know, it's which is we are on the Eastern time, and then you know, for this, welcome to the Wayne State College of Engineering Global Engineering Education Jessup Seminar Series. And today is the first speaker for this whole series. We first take this opportunity to thanks our sponsorship, you know, including Nancy Philpott and the Thomas McGill Center for Global Engineering for hosting this, and also for the Jessup, you know, the sponsor the seminar series. And I know some of you probably is registered attending this event, you know, globally, you know, probably, for example, in the East Asia right now is late evening. So I hope that, you know, we will try to make this on time so that everybody from, you know, globally can attend this. In case you couldn't, you know, attending the whole seminar series, most of these lectures, I hope that we will have all of them will be, you know, we will have recorded, and then we will put it online. So with that, we were starting today's the first speaker. We are very happy to have Professor Jeremy Rickli from Industrial and System Engineering. Sorry for the typo that we're still using the old name in the when we make the flyer, but we will correct it soon. So his talk is more focused on the what we call the disassembly. Basically, is, you know, manufacturing, remanufacturing, and for the sustainability. You know, this is a very important topic in today's world. Globally, people almost everywhere, you know, when we're talking about engineering, we're talking about the sustainable engineering, etc. So we are very happy to have Professor Rickli to starting today's talk. Just a very brief, you know, introduction about him. I'm sure that he probably will be mentioning a little bit about this during his talk. So Dr. Rickli got his bachelor and master degrees from Michigan Technological University, which is up north in Michigan in 2006, 2008, respectively. After that, he's spending 5 years in Virginia Tech and got his PhD in the industrial and system engineering. You know, joined the Wayne State immediately after getting his PhD. And right now he's a social professor leading the Mars Lab. You know, the Mars Lab, he probably also going to explain what does Mars Lab stands for, but it's a very you know, timely topic related to the global sustainability. So without further ado, I will turn the podium to Jeremy.
All right, thank you, Wei Song, for the introduction. I really appreciate it, and I thank you for the opportunity to give this seminar. Disassembly is an area that I'm pretty passionate about. Spending my research kind of tool bag for many years since I started at Michigan Tech. In IGER, so it was IGER, NSF-funded IGER Institute to really teach or train a generation of PhD students and graduate students at the intersection of engineering and public policy, because they felt that for engineers to kind of have an impact on sustainability, they had to have some education or some knowledge of the public policy, how public policy is formed, to see how engineering insights might transfer over to actual public policy to impact the broader society. So it's always been a very fascinating topic. I'm hoping that the presentation, the seminar that I can give today will at least inspire a little bit of interest in disassembly if you don't already have it, or remanufacturing or recovery. If not, that's okay. Maybe there's a couple pieces in here that stand out. I think so. With the seminar, I have about an hour and a half. I'll try to keep to time, maybe end a little bit early, and we can have a pretty good discussion, question and answer session at the end. To start, before I kind of read off the title, the Mars Lab, so it's Manufacturing and Remanufacturing Systems Laboratory. With all the new advancements on Mars, I think I get a lot of searches and hits on Twitter and Google that aren't actually for remanufacturing disassembly, but something that I don't do work on, which, traveling to Mars. So today I want to give kind of I'm not going to say a broad overview, but I want to hit on a few different areas in disassembly and focus how disassembly fits into the circular economy. And really that's looking at 3 different areas: design, use, and recovery life cycle stages. So what we try and do in the lab and with some of our research is connect these different pieces to really make disassembly something that we want to think about at the beginning, something that we can deal with at the end if we haven't already planned it into the design of the part, and something that we can leverage our new incoming data from Internet of Things to try and make better decisions on products as they come back. So that's why I talk about coordination between design, use, and recovery lifecycle stages. And really that's to fit this and to get it into the circular economy. So I'm going to give a little bit of introduction material. I'm not sure how many are familiar with circular economy. Maybe you've heard the term. Maybe you know about it in depth, but I want to give a few slides just to get everybody on the same page. So the graphic that I have on the screen right now is one of the models or one of the graphics used for the circular economy. And the first thing I think that you'll notice in there is just all the feedback loops, right? So that's where the term circular economy comes from, is you see parts being produced or items being manufactured, consumed by consumers or used by consumers, and then feeding back into the system, right? Creating these circles at different levels. And so in this figure, and I'm going to change it here in just a minute, we see 2 different halves. We have one half with a user and then a consumer, and then we see biosphere, biogas, biochemical feedstock, farming, collection on one side. And on the other side, we see really mining, materials, manufacturing, maintenance, reuse, refurbish, remanufacture, on the right side. So this side's speaking more to kind of our consumer products, our automobiles, our computers, heavy equipment, aerospace, airplanes, engines, anything that falls into that category, which is where I usually focus on. But at the bottom, we still see energy recovery and landfill kind of exiting the system, right? These aren't providing our circles back into our service providers or manufacturers or the materials manufacturers. And the circular economy really aims to advance those feedback loops. So how can we really avoid things going into energy recovery and landfill? And for me particularly, it's looking at discrete components, so not chemicals, not as much materials, but products that have multiple components that are assembled together, multiple materials, multiple functions, multiple lifetimes. And how do you really go from this materials and manufacturing, and how do you plan in the design and in the use and in your operations to make these feedback cycles really operate efficiently? And there's different levels and there's different options that you can choose between remanufacturing, recycling, and reuse, and maintenance. So maintenance will be sort of extending the lifetime of whatever item or assembly you have. Reuse, redistribute doesn't really put any more value, doesn't add any more value into a component or product. It basically brings it back into the cycle for another lifetime. So, I think one example is plastic shopping bags. Sometimes you have people that collect a lot of them, then they reuse them to make bags. Like larger bags to carry groceries in. So that's sort of a reuse side. Refurbish, remanufacture really aims to add or to recoup some of the functional value of the product, to make it act like it is a new product, to give that same sort of quality, same sort of performance. So you are putting in some value, adding some reprocessing to the part in order to make it almost act like new. In the remanufacture, reuse kind of phase, in some areas and in some communities, it's called retaining the functional value. You're not breaking down this component into its fundamental material. You're not shredding it. You're not melting it down. You're still using the same basic dimensions and function, but you're actually retaining it and sending it out for a second life or remanufacturing it so it's almost like new. Now recycling usually classified as retaining or recouping that material value. All right, you're kind of, maybe you're melting down, you're shredding the material, so eliminating the original function that component was for to get at that basic material. Now, one thing that I kind of want to zoom in on here is these steps. So user, maintenance back to the user, reuse back to the retailer service provider, and refurbish, remanufacture back to the product manufacturer. Recycling goes back up to the materials manufacturer. And where we focus on, and where this talk is going to focus on, is really the steps to make that happen. So the steps that happen at these facilities. All right, what does it take once you have it collected by user, once a remanufacturer or core collection agency or recycler has it? What do they really do with it to access that value that exists in those parts? How do they more efficiently get to that material value, get to that functional value in the specific components? So really, it's going to zoom. This talk's going to focus on how we make these processes better that's happening in these entities. Now, if we could even dive deeper into that, we can look at the stages that will happen at the maintenance or reuse or the remanufacturing entities. So on the top here, we still see input supply. So this would be like the top materials product manufacturers here. The use phase, so that was the consumer in the last diagram. And then discard is the landfill or leaving the system, leaving the circular economy. Now in the core collection, this is where the process for recycling, remanufacturing, maintenance, reuse begins. And if we break out the steps that happen during that phase, we have sorting and testing, and that's to determine how much value might be left in the parts. And if there's not a lot, it might go to disposal. Disposal could also mean it goes straight to recycling, where you're going to shred it and use that material. And if not, it'll go to disassembly. And in any case, you are going to get to disassembly at some point, where you're breaking out this larger assembly into specific materials and components to test those. Now, if they do have some value, if it's determined that there is a path forward for those parts, they'll go into cleaning, inspection, fabrication, where you may do some sort of repair to the part with a variety of different processes. You may have to add new components if there's components that just don't have any value left. They don't have any functional, they are worn to the point where they can't be remanufactured or reused. Then we would input new components. So you'd have this mixture of new components, old components, go to reassembly, testing, and then back out for distribution. Now, within this whole system, disassembly ends up being a very key aspect because it's how you take what you've obtained from customers, how you break it down into the individual components that will give you value, and what decisions you're going to make to do with those parts. So am I going to invest in remanufacturing it? Am I going to just invest in recycling it or send it off for recycling? I have to make that things being pinched, so potentially in supply, that we're not getting enough material back. In disassembly, if the process is typically manual, and if that's slow, then that will limit how many cores and how much material you can actually break down and how much you can push through into your remanufacturing recycling system. So there's a lot of work, interest here in disassembly to make this easier. So there's less costs, less work associated with getting to these valuable components once they're done with their use phase. So what is disassembly? Wei Song had mentioned kind of what disassembly is and how it fits into the system. I want to bring one definition that I'll kind of keep consistent with the rest of this talk, and it varies a little bit depending on what literature you're reading. But here we're going to classify it as the process of physically separating a product into its parts or assembly. So that's what I'm going to focus on with disassembly. And our research really tries to get at how we can make those methods better. So how can we plan those methods better? How can we automate it? How can we, how can we design that into the system? But why do we want to do it? So yes, it fits with the circular economy. Why is that good? Well, the first reason why is reducing environmental impacts, reducing the burden on the environment. So keeping those materials in the loop, not sending them to landfill, to try and eliminate those environmental impacts that would happen if you just dispose of those components, potentially toxic materials, heavy metals, avoiding those going back into the landfill. Now, the second reason is cost. And this is for some materials that you have some trade-offs depending on what material you're looking at. But the cost of manufacturing some materials is very expensive. The cost of remanufacturing those materials or components is significantly less. So if you can have access, if you can get to these components that you can remanufacture, the investment that you need to put in to remanufacture these parts is less than creating a new one. It's not the case with all components or all products, so it's sort of a case-by-case basis. Some small electronics, right? Those materials, really you want to recycle them. You want to take it back to the material value. Components like heavy equipment, earth-moving equipment with large metal pieces, right? The investment to make that metal piece, that engine block at the very beginning is very high. The investment to remanufacture it is fairly low, the cost and the environmental impacts. Now, the third reason I have here, and I put up this logo for the Critical Materials Institute. It's a Department of Energy institute, and they focus on how do we secure our supply base of critical materials. So critical materials being rare earth magnets, lithium. These materials are essential to the advancement of new technologies, or they're being used heavily in technologies that we see out in the next 5 to 10 years. Unfortunately, those critical materials, the supply base is usually very small or rare, all right? So hence rare earth metals or rare earth magnets. So the Critical Materials Institute really researches substitutes for those materials, different ways of manufacturing those materials, but also ways of taking those materials that are out in products right now and recouping or getting those materials back through recycling and recovery. Now, one reason they want to do that is if we're developing advanced materials, you want to have a secure supply base for those critical materials so that your manufacturers or country can actually leverage those materials. Now, disassembly is one way to access a supply of those materials that really isn't, being accessed as much as it could be right now. A lot of focus maybe on getting new materials, finding new mines, or no resources for those materials around the globe. But there is quite a bit of material in used products, in current products, that with the right disassembly methods and the right scale up, the right research, you can really increase that supply. So what's the problem? Disassembly kind of hit on a lot of different research areas, but what's the main problem within this whole area? And one is that we have manufacturing here on the left, my nice little icon of a factory. And then we have repair and remanufacturing on the right. And really a big question mark is we don't really know what happens in between. And there's a lot of different things that happen in between these two areas. So everything that sort of happens between the factory and when it's collected by the user, by the consumer, changes how the product functions, changes what value is left in the product. It changes how you can actually take that product apart, and all that information is unknown. And so we have a few different ways to address that I'm going to talk about, but that's really the main motivation for my research in disassembly is if we can either reduce some of this unknown uncertainty that happens in this stage, or we can plan for it, then we can make the operations at remanufacturing, recycling, disassembly more efficient. If we can make them more efficient, hopefully we're pushing this kind of circular economy recovery into the model where it's profitable, right, or more profitable, where the incentive to do it is there, and it doesn't have to be or isn't necessary to be sort of a public policy initiative. So we don't have to require that companies deal with their products at the end of life. They will want to anyways because there's an actual business case there, along with an environmental case. So if we go to traditional manufacturing, what that looks like or why we don't have that information or that sort of unknown is because manufacturers are able to release specs. They're able to have contracts with their suppliers that X amount of parts have to be delivered in Y quality standards. And so you have these negotiations and these contracts between your manufacturer and your suppliers, and their contract, their performance is based on delivering these materials and products at a certain quality, and that can be controlled. So you're able to really have a known of what's coming into your factory. Now, broadly, and this isn't the case everywhere, broadly for remanufacturers, their system looks a little bit more like this, right? They have their recovery operations, and then you have all these different consumers that are returning their products or that someone has bought in order to be recycled or remanufactured. So now you don't just have 4 suppliers. You may deal with maybe a distributor who can give you a mass amount of cores, but they're collecting from a broad array of consumers who use the part differently. Maybe it's the second or third use. Maybe it's the third consumer that's had the product, right? A used car that's gone through a couple hands. And now it's coming all back to the recovery operations. And so now they're trying to deal with all of this uncertainty, all of these different suppliers with different performance, different use cases for it, different environments. You could have a car that's at 100,000 miles. You could have a car that's at 250,000 miles, right? And so they're trying to deal with all this to make some sort of business enterprise where they can reduce this unknown or uncertainty through disassembly, cleaning, inspection, and then have the processes to add value back to that part and send it back out. So the goal that we want to do in the lab is really research methods that take what we see now with value recovery and really push it more into traditional manufacturing. And not, I would say push it towards traditional manufacturing, but really lessen these unknowns, right? So make it more consistent so that the remanufacturers know what they're getting, or they have a better way to deal with the uncertainty that they're giving here, so their operations downstream flow a little bit better or more efficiently. How do we do that? And this is where I'm going to focus on for the next hour or so, is 3 different ways. And so this talk is divided right about disassembly, but I've divided it into 3 different ways that we target it in the lab. One is planning, and that's going to be kind of a mix between the stages: use, recovery, design. Is what do we do about planning for disassembly? Whether we're planning for it at the design phase, whether we already have the design, I'm going to have to remanufacture a lot of these parts, I'm going to have to disassemble them. How do I plan for it then? Next is automation. So where does automation fit into disassembly? What are the challenges with it? Are there opportunities there to really advance disassembly by some sort of automation? And then lastly, we're going to get to design. And then as I go through, I'm going to try and tie all these together to show how planning can really impact your automation. Automation can kind of affect how you want to design the part, and then design could really help you out with planning and automation. So there's sort of all these different connections, and they feedback with one another. It's not just that design will feed down to automation, that'll feed down to planning. There really is sort of a feedback here. Now, we're looking at these, I would say right now, kind of separately. We have some planning work, we have some automation work, we have some design work. But one thing that really interests us and myself is really integrating these. So how do you get that feedback from automation? How do you incorporate that back into design, and how does design then come back to feed the automation side? So first is disassembly planning. I'll have a couple case studies here and some work we've done in the past for this. What is disassembly planning? Really, it's all aspects of in what manner. So here, how many and what to disassemble, along with how you optimize disassembly based on some objective function. So really, we're really focusing on how do we disassemble it? It already exists. If we're increasing the scale to maybe the supply chain side, how many do I want to disassemble? How many do I want to collect? And then in some of the decision cases on the business side, what do I really want to disassemble to maximize my profits? Now I'm going to focus here on in what manner, which really is termed disassembly sequencing in the literature, which is I have my assembly, I have all these components fastened together or assembled together using various methods, welding, bolts, rivets, whatever it might be. What is the best way that I disassemble this? And it's really termed disassembly sequencing. And initially, and for, I guess, kind of a rough summary, it's a shortest path type of problem, right? How do I get from my assembly right now and in the most efficient, quickest way, get to the parts that I want? It could be you want to disassemble everything, so that would be called complete disassembly. I want all of my components, every single one out, so that I can try and get value from those. It could be selective disassembly, and this one is where you're really honing in on a high value piece. There's a specific material that's extremely valuable. There's a specific component that has a very lucrative secondary market. What's the best way for me to go from the whole assembly into that one specific material? And then partial disassembly, which is more on the theoretical side, I think, than the practical side, based on some of the literature, which is just give me the best way to disassemble it. Tell me how I should do this to optimize or to maximize my profit or to minimize my cost. Where should I stop? What parts should I recycle? I don't want to disassemble everything because that's cost in terms of labor, that's cost in terms of processing, especially if there really isn't any return after disassembling after a certain point. So let's use optimization, let's use industrial engineering methods to really determine where do I want to stop? Where's my best stopping point? Now, typically, this has evolved from mostly a single objective, minimize my time, minimize my costs of disassembly, maximize my profit or my revenue, and it's evolved into a multi-objective disassembly sequencing problem. So now we have disassembly methods that optimize or the environmental impacts, minimize the environmental impacts while maximizing your profit. Or we have multi-objectives methods that try and maximize your throughput in a disassembly line while minimizing your energy usage or minimizing your time. A lot of methods have really been focused on deterministic values. Always going to get this amount from a component. It's always going to take this amount of time to disassemble something. Unfortunately, literature has identified that that's maybe an assumption that you can make, but maybe isn't the best assumption because of the uncertainty involved with the products that you get back from consumers. And that uncertainty is really classified as uncertain quality in the product. So if I have two components back, two assemblies back that are the same, one's been used more, it may take me more time or more force or more energy to release a bolt in one product than the other product, just because of how it's used. So that'd be uncertain quality. Uncertain quantity, I'm not really sure how many I'm going to get back in some systems. So I may have a demand for a certain part, but my supply coming in is kind of an issue. I'm not sure how many I'm going to get back. So I need to plan for that uncertainty. And then timing. I'm not really sure when I'm going to get back. So what is the best window for me to collect these parts? Where's my prime market for the remanufacturing side? If they come back too late, maybe there really isn't a market for it and I can't really sell it. So there are a lot of issues that go from just the disassembly, in what manner do I disassemble it, all the way to your kind of business model, right? Is it one where it's more of a service system where I will control the use phase of it, record the maintenance, so I know exactly what happens at the end of life? This is sort of like the Xerox printer copier model. Or is it one where I kind of just produce the parts and I send them out, and then I rely on maybe develop third-party markets, third-party landfills or scrapyards to really do it? And this is how some of the automotive side has operated, where there's a very rich secondary market for automobiles. So there's scrapyards. There's a lot of people doing remanufacturing and disassembly for those. So what is the disassembly sequencing problem? And I'm going to kind of really generalize it here, or try and give three components that all disassembly sequencing problems have. One is some sort of model, representation of the disassembly of your part, right? So somehow you have to characterize, not just in this part, this part, this part, or in a bill of materials. You need to have some characterization, some representation of how these parts are related or how the components are related, and what operations it takes to take those apart. Then you have some sort of objective function, and this varies. You could maximize profit, you could minimize time, you could minimize environmental impacts. Throughout literature, and there's a rich array of disassembly literature and disassembly sequencing literature, there's a wide variety of objective functions, and there's always new ones coming out as we're studying, as the people in this field are studying different problems with disassembly. So you have your representation, you have your objective function, then there's some sort of solution method for disassembly. It's an optimization algorithm, some sort of simulation, whatever it might be. But this is how disassembly sequencing problems, if you're interested in them, so this might be someone considering research or someone that's done research in this area, this is kind of how each one is set up for disassembly sequencing. And it really hinges on some of the incoming data for the disassembly. The objective functions, the solution approach, especially a solution approach, can be pretty general. You can pull from some different areas. Objective function you can change. But really, an essential piece of this is the data of how you represent disassembly. And I'm showing one version here, and I haven't seen any studies on what's the best version. I think it's personal preference, and sometimes it just depends on what part you're doing. But this is what we would term a directed disassembly network. So here at node 1, this node would represent a fully disassembled or a fully assembled product. So your engine or a coffee maker, as I'll kind of get into later on, complete how you would use it. And then each of the nodes represent some stage of disassembly. So this would be stage 1, stage 2, maybe stage 3 or stage 5 as you get the very end. Now those stages are characterized by an assembly, the parts that are still remaining together, and then some part that that you've taken off, represented by A. So A here would be an arc. I would take off this component of the product first, and that would take me from disassembly stage 1 to disassembly stage 2. This is a model that can get very complex and very large depending on the product you're doing. But we're able to translate this directed disassembly network into basically a matrix representation. Could be ones and zeros, could be something else. But this information is really what we can input into our solution methods. And this allows us to determine, can we disassemble it in that way? And if we can get that information, we can determine what the cost might be of disassembling in a certain way. It also gives us a way to check different disassembly sequences. Is it feasible? Can we actually achieve our disassembly goals with that sequence? And does that lead to a better objective function? So that's really one of the main values. Now, the objective functions, they can vary. You have ones that minimize the environmental impact, or you have some objective functions that really focus on cost. And this can be a wide array of different variables or parameters within cost or profit. It could be maximize your profit. In this case, I know we have like 4 different functions here, but really what I want to do is understand how my profit or my revenue varies depending on my sequence. So can I determine a disassembly sequence that makes my profit or revenue more reliable per product or overall, so that I know that I'm gonna get maybe $5 or $2 on most every part I remanufacture? Or am I going to change my disassembly so that I might lose some money on some parts, but I might have the chance for overall larger revenue after I consider all the parts that I disassemble? And then the solution methodology, the one that we've implemented is a genetic algorithm. There's a variety of versions of genetic algorithms. But in this case, the genetic algorithm will basically search through different sequences. And as it searches through those sequences, it will evaluate what the profit is, what the environmental impact is, what the variability in the profit is, whatever your objective function is. And then from those solutions, the way the genetic algorithm works is it generates new solutions. So it tries to slowly improve those existing solutions or existing sequences that you have. So what we'll do in our methods is we'll generate kind of an initial set of disassembly sequences, randomly generate them. And then with this method, that randomly generated set of sequences will slowly improve. And eventually, as we make these small changes, small improvements, we'll get to sequences that are both feasible, that maybe maximize profit, maybe minimize your environmental impact, or whatever, some other objective, minimize time, minimize cost. And it does this by changing small values. So we'll go through and we'll change disassembly sequence. Maybe I'll disassemble part 1 first in one sequence, and then another sequence I'll disassemble part 2. And we'll make those small changes and begin to search through this whole space to try and find those disassembly sequences that really achieve or have a performance that we want in our system. There's a lot we can go into depth about genetic algorithms. So if you have questions on them, please let me know at the end, and we can kind of come back through here and go through how this would actually run for the disassembly side. But how do we use this to actually research disassembly? So, you could do the optimization, give my parameters, and maybe my business would run better, hopefully. But what do we really do in the research side with the sequence optimization? So one that we've done in the lab is really investigate the environmental and economic trade-offs. So in this case, we took a coffee maker, just a really basic one. It's not an espresso machine, doesn't have too many components, plastic, glass, a little bit of metal. And we started with that coffee maker, and ask the question, what's the best way to disassemble it so that I can minimize my environmental impacts, but still have some sort of economic advantage here? If the market was right, if the labor costs were right. The first step in this is that data side, the model. So that's the first thing that we need to do the disassembly sequencing. And in this case, because we have even just a coffee maker, we have multiple levels. So in this case over here, it's a very simple disassembly network. It's kind of trivial to have it up here, but this represents taking the carafe out of the coffee maker. So that's first. Now I kind of have two separate products. I have the reservoir and I have the carafe. And that's what's represented by these two pieces here. All right, so I have the carafe here, and that's disassembling the handle, disassembling the top. And then I have the reservoir up here. Now, once I have the reservoir here, I then have another subsequent subassembly that I need to model. And now we get down to a more complex disassembly model. All right. So in this version, we have sort of these different hierarchies of our disassembly data. Now, where we really focus on is more here, because this is where the optimization can be very helpful in searching the different paths that we see here. And now we want to apply our method to these different models to say, what sequence do I really need to choose? Do I have some trade-offs in the economic and environmental side? Now I'm going to show the end results. There's a lot more details in this if you're interested. We took the multi-objective environment economics, so we had dollars, just a monetary value for the economic side, and then we had impact points here, negative 0.087 or negative 0.03 to represent the environmental impact that were generated with lifecycle assessment software. Now we ran the optimization, we did the process for each of those hierarchies of disassembly levels, and then we aggregated all the results. Now I'm showing three results here on this graph on the bottom right. So we have A is the case where you're maximizing just your economic side, and then B is the case where you're completely minimizing your environmental impacts. And what we're able to find is this trade-off, this sort of sweet spot in the middle, where you could balance out your environmental impacts and your economic impacts. Now you can move forward and look at a lot of the variability. How does the variability of incoming parts really impact your business, impact how you want to disassemble it? How does the age of my products impact how I want to disassemble at my value recovery facility? So in this case, we took a solenoid valve. First step, again, was converting it into our disassembly data, our basic network here. And then we said, what can we really do with that? How can I really investigate these impacts of what happens during the use phase in my optimization, in my decision making for my sequence planning? And really the way that we did that was by changing the age distribution of our products. So changing what our profile of products in the use phase look like. So in this chart here, we would see this line here going down. This would be kind of a brand new product coming out. All right, most of the products are relatively young. They haven't been out in the use phase for quite a while. And then as those products age, we're looking around this curve here. Our company stopped producing it, so we're not releasing any new products out. Now most of the products that exist in the user are around 3 years old, right, following some type of distribution. And we can continually increase or change that distribution so we can get out to the point where this is now maybe a legacy part. We're not manufacturing it. We don't have the plans. Most of the products are fairly old. They're going to be fairly worn. Now, as that population ages, each component within that product is also going to change in value. And so here we have these value curves as the component ages. And you'll see as this product here, the bottom casing that we call it for the solenoid valve, it starts out as a very high value product, the metal piece that maybe has a lot of resale, recycling, remanufacturing value. And then it's decreasing around in years 8, 10, it's decreased by about half. So we take those two data points, and then as we increase this distribution in our model, in our sequence optimization, our disassembly is going to change. Our sequence is going to change, and our potential profit or our costs are also going to change. Because as the products are out here around age 8, we can see that the value profile or the value of those products really changes for the manufacturers. Now, what can we get to it? Now, I'm going to show a couple plots here, but really what we want to learn is the trade-offs. All right, so the lines here aren't really, there's a lot of details in the lines that we can get into in the discussion side or later on. But really is we want to investigate these trade-offs. So in this case, we have the probability that I'll have a profit on a specific component versus my total expected value of what I could get out of the business, right? And we're seeing this sort of relationship change depending on your sequence, depending on what age distribution you're at. So in this case, we see the X's. This is for when a product has been released. It's not really being made anymore, but it's still relatively young, versus maybe these diamonds here. This is when the product would be newly released. So this can give some insight into how me as a disassembler, as a remanufacturer, how my business is going to sort of change as these products age out, or when they're first introduced to when they're aging out. And we can do that for the expected profit and how uncertain that profit might be, right? And we're starting to create these lines for each of the distributions, or each of the stages of where that product's at. And that gives us a sense of the Pareto frontier of where we can make our decisions. So if I see this dotted line here that the laser pointer is following, my overall kind of multi-objective value is pretty similar for all those different values, or all those different cases. And now it's up to me as a remanufacturer to decide where I want to be on this curve, right? Do I want to be down here with very low variability, lower expected profit, or do I want to be up here where maybe have more variability in what I might have coming back, but my chance of making a better profit is a little bit higher. So now what? All right. So we have it. If you have this disassembly sequencing capability, you have your model, you have your objective function, you have your solution methodology. Really, you can do you have a lot of possibilities. You have a lot of ways that you can change or model different problems that evaluate different scenarios, different business scenarios, a service system, an incentive program to get products back. And we've started investigating a little bit of that. So with that core kind of functionality of with the coffee maker with the solenoid valve, what I can do is I can modify some of my parameters and put in there, what if I offer the consumers X amount of dollars for their product? What do I expect to get back? All right. I can integrate that decision model from the consumer and make an estimate that, well, if I offer $5, I would expect that we will get these products back, that a consumer will see that $5 is worth more than what they have in the product right now, and we can expect to get those returns. Now, that's one way to try and induce some control into the system so that variability or the unknown between the manufacturing and the collection is reduced a little bit. You can also add a little bit more depth into regional impacts. So what's the intensity? What is the weather in a certain area? How does that impact how my product might be disassembled? So in this case, we haven't integrated this with the optimization method, but we've looked at if a product was used in a harsh weather climate versus a kind of a moderate weather climate, how does that intensity change how the value of those products are going to be at the end of life? And then subsequently, if we can put that into the model, then we can plan our disassembly accordingly, so we can make sure we tailor it for those parts that we receive from certain countries or from certain customers who have a high intensity use for it. Or potentially look at triage, and triage meaning if I'm getting a large batch of cores back, what do I do with those? If it's going to really put a strain on my system, I may need to make some quick decisions on what products that I collect I actually remanufacture, which ones I disassemble, and which ones maybe I scrap or recycle because I just don't want to store them for months or for weeks or potentially years, depending on how the business operates. So with that kind of core sequencing functionality, and there's quite a few of them out in research literature, you can do a lot with investigating different plans, different business models, different scenarios to help plan for disassembly a little bit better. A lot of that's given a product or given a case. So it doesn't really feed back into, all right, how do I actually change my product to account for some of these cases? So what's next? New objective functions. You can put in fastener designs. You can put in disassembly direction. One fascinating area is tracing product usage data. So if you can integrate, if you can get access, easy access, efficient access to that data for the use phase, any remanufacturer is going to have a much better idea of what they need to do with that product at the end of life. They're going to have a much better idea of how much they can make off of it. But kind of no matter what you do with some of those objective functions, the disassembly planning is really still centered around this model that represents or characterizes how you disassemble it, what you can disassemble first, what you can disassemble next. That's a fundamental piece of data that you need. The objective of what you want to study or how you want to modify that sequence to achieve a certain goal, and then the solution method, depending on what type of objectives you have. How quickly you want a solution, selecting that solution approach is another important decision in disassembly planning. So kind of abrupt, but I want to shift over to automation, and I'm going to try and tie all these together at the end. But the automation side really comes in because of scale up. And critical materials becomes a very significant piece of this. If you can scale up the disassembly of critical materials, you can have a supply base, a brand new supply base to feed into advanced technologies, and to take advantage of some economies of scale. Really, it's about efficiency. And if disassembly can move over into some sort of automation, the amount that can go through this process, the amount that they can produce, that they can disassemble, remanufacture, starts to tip into the point where it's more profitable, where they have enough to sell that it'll be more of a business enterprise, and they won't have to deal with some of the uncertainties manually. But the issue is still that unknown. And the unknown that we're going to add into the automation side isn't just the quality of the product, but it's what product you're trying to remanufacture. So in the cases of remanufacturers, they're taking products from multiple original equipment manufacturers. So the designs are slightly different. They might have different fasteners. They might have different accessibility. They might have different disassembly precedence charts that we showed, different networks that characterize how they are disassembled. The torque, the amount of energy required to remove the fasteners might change. So these are real barriers to the automation side, and barriers to really increasing how much you can disassemble, how much you can remanufacture, and how much you can push through. Now, if you can address these challenges, and especially for critical materials, you can get to a volume where the supply of those rare earth magnets really contributes to the total supply into new technologies and into new materials manufacturing. But really, you need to have some new agile way to do this type of disassembly and to automate it. And so what we're looking at Wayne State, and this previously was a collaboration with Oak Ridge National Lab, is collaborative robots as an automation solution for disassembly. And we're studying what type of performance gains or what type of different performance you can get out of leveraging collaborative robots in multiple facets in the disassembly side. So collaborative robots, if no one's familiar with them, if you've heard about it, they're typically lower volume, higher mix, so they have a bit of flexibility. They're a little cheaper than really large integrated robot systems, easier to deploy. Ideally, it adapts quickly to the environment, so an operator can reprogram it right on the fly there through teaching it by kind of hand guiding this cobot to program it. They have lower speeds, lower payloads, so you have a trade-off there. They can't handle as much. They usually have safety mechanisms in place so you remove the fences so an operator can work directly with them. That's opposed to typical industrial automation or industrial robots where you're going to have fences. You have a significant amount of upfront programming into the system. It's going to try and repeat this process over and over and over again. So for disassembly, the characteristics of a large industrial automation system don't work because of all the different products that you have to disassemble, the different fasteners, the different types of fasteners that you see. So we need to move it down into maybe the collaborative robot side where things can change quickly. Vision systems also play a part of that, recognizing what type of fasteners are coming, what type of parts are coming. It really is sort of a scaled kind of approach that really takes advantage of what the human can do and what they do now with manual assembly, and try and bring in the ability to scale up the volume of the collaborative robot. Now it requires planning in this sort of coexistence between the disassembler, a human disassembler, and the collaborative automation. So what type of shared workspace do you have? Ensuring that you have collision detection safety features active, that your workspace is designed to potentially avoid this collision. That your actions are coordinated, and there's a lot of research in this area outside of disassembly, right? Human human-robot interaction, human intent with a cobot. So there's a lot more research there outside of what we're doing in the disassembly side. And then active learning. So an operator actively changing the cobot, changing the program of what they have to do to take care of new parts that are coming in that need to be disassembled. So some samples of how they're used in just manufacturing is a screwdriving at Bentley. So this, I'll remove the fence and now the operator can operate or work right with the cobot. A BMW assembly line where the human's right in there with the cobot. Masonry, so doing wall construction and bricks are helping the mason lift the bricks, position the bricks into place. And material handling is a large one, so assisting with pick and place operations or doing pick and place while the operator is doing some action at the table. So there's a lot of possibilities here, and where we're looking and where we're researching of how cobots fit and what they can add to the disassembly side is really from two directions. One is a task assistant. So this is a cobot actively assisting with manual disassembly. That's doing this all day, every day, right? So we just have a lot of parts that we need to disassemble these materials. The cobot's going to assist that to improve the efficiency to help with some of the guidance. So it could be pick and place while the operator can focus on certain parts. It could be that the cobot will handle some of the repeatable fasteners that are shown, but the operator will jump in once you see a fastener or an disassembly action that really is unknown, that it hasn't been programmed for. And the other way is a teaching tool. And this is to really reprogram, I'll say reprogram, but to allow your disassembly line to learn how to disassemble new parts faster. And that's the one we've started looking at, that we've made the most progress on. And it's really the ability to quickly shift or quickly reprogram your line to new products coming in, new parts coming in that need to be disassembled. So in this work, Oak Ridge National Lab through the Critical Materials Institute was developing the large scale line model that you would see here. So this would disassemble alternators that had rare earth magnets at a very high volume. And then we at Wayne State, we're researching how we can take the cobot, the results of a cobot or a collaborative disassembly with a human, and feed that information back into this large scale line so we could immediately change parts. So if we had a product, an alternator coming in from a Toyota, it would have one disassembly action. If we had a Hyundai one coming in and it was slightly different, we could rapidly reprogram or characterize that disassembly sequence, that disassembly information, and send that to the line at the appropriate stations that need to do the actions for disassembly. And really what it was is getting, how do we fit this human in the loop between our large scale line and our cobot, right? And that's the work that we really focused on. So here in this image, we started with simulation before we moved on to an actual cobot. So we had a software called Visual Components. We were able to develop a cobot disassembly station in the software where we were able to export the actual positions and trajectories and motions of the cobot along with the actions of the user. And then we were developing and researching a method to transform that data that we would collect from this user disassembling with a cobot into the information that you would need to send to the large scale disassembly line. So in a sense, that original information that I showed, that directed disassembly network that I said is kind of one of the fundamental pieces that of what you need for disassembly sequence planning. At the very kind of lower level, that is what we wanted to learn from this disassembly action or disassembly with the cobot. There's some other things that we wanted to take into account, which was disassembly direction that I'll talk about in a couple slides to give specific directions to the robots in the large scale line. So every new assembly that would come in, every new model that would come in, an operator would work at a station with a collaborative robot. They would disassemble the part, and that information that would be collected by the cobot will be sent to the central planning server, central planning place for the disassembly line. And that information would then get distributed out to the automated large scale disassembly line so that the correct robots and the large scale line were doing the correct actions in the correct way to disassemble this new part coming in. So conceptually, we would have first this human to cobot where we're doing the learning. That would be sent to the database where it would interface with the planning software. What is the schedule that you want to keep? What is the demand for certain parts? How much material do we want to produce? So that's going cobot to the digital twin, to the simulated virtual line and virtual capabilities. And then the decision-making processes here in the digital twin would then relay the information, the task information, to the robots that had to do specific disassembly actions. So that when that new component came in for disassembly, we could quickly change it, or we could quickly program the line so that that alternator, that part, went to robot 1 for this disassembly task, went to robot 2 for this disassembly task, and then eventually completed its disassembly operations in the large scale line. Now, when a new part come in, you would repeat this again. And when a new model would come in, when the next year's model of alternator would come in, then you would repeat it. And in that way, you're not reprogramming every single robot in the large scale line. And if you have to switch between batches, depending on what supply you have coming in from the users or from your core distributor who might collect these for remanufacturers, you could easily and quickly switch between these. So our main challenge was really translating, to start this, was translating that cobot data, the human data, into disassembly tasks. So what is the disassembly task? I want to identify that it's unscrewing. I want to identify that it's just removing a pin. And then what are the actual directions for that task? So that's really where our methods kind of focus on. One was pick and place and one was unscrewing, and translating all that cobot information into those specific stages. So we'd record the trajectory. So we'd have exactly where the cobot is going, where the user is guiding that cobot. We'd have the speed, we'd have rotation, and then we'd also have signals from the operator. So once they disassembled the piece, the operator would basically put a check or a link in the cobot trajectory code. So we knew that the operator was giving us some feedback on changing or disassembling a new component, or disassembling a new component in this direction. And then we were able to take all that information and translate it into actual directions of disassembly. Now we moved on from the virtual side to an actual physical experiment. So this is a UR5E cobot. This is the one that we use. Here it is doing collaborative disassembly for a small 3D printed piece. It's kind of a fun, interesting thing about this picture. So once we had the cobot, was actually last year around February or March when it was delivered. So we had no lab access. So I was actually able to get it delivered to my house during some work with Wayne State. So in my basement, we were actually operating this cobot, or I was operating this cobot, and trying to get this code out so that we could continue our project with Oak Ridge National Lab. So we have the cobot here collecting the data, and then it's fed back into our automation software, where we can then extract the trajectories, extract the motions, and then from there determine what type of disassembly task was being taken. So as we progress on this, we were comparing what we had done, our method developed in the virtual side, with the actual human. And we wanted to really do this comparison because once you start putting an actual human into operating the cobot and guiding the cobot, you're not going to always get the exact same position. So before we sort of implemented this into the line, we really wanted to find out what uncertainties, what variabilities a human operator would induce in this system, and how that might impact the disassembly side, or the disassembly information we really wanted to take. So we have, a couple matrices here, but in a sense, what these two tables are doing is comparing the virtual side, where it's perfect motion, exact, coming down exactly at 90 degrees to a part surface, versus what we collect from the actual cobot and the human doing it. And what we learned is that we would have to add or research a method to really account for some of the variability and small differences that a human would induce into the cobot and into the trajectory planning. So a human may have an angle for a cobot to remove a fastener here, and that angle may not be perfectly 90 degrees, but the fastener would still come out and the cobot would still complete the operation. Well, as we're working on this, our aim is was to have a solution for this, because once it gets into the large scale robots, we want to avoid this type of angle difference. So we want to have it be 90 degrees from the surface, so you can more efficiently take that fastener out and you won't have any errors or hopefully no issues when this gets sent to the large scale line and it's doing this disassembly over and over again. So this is something we're still working on, is how do we really account for this variability, and what's the impact on the disassembly side of it. In addition, things we opened up, we were able to get back in the labs at the beginning of the year. So we were able to move the cobot back into our manufacturing engineering building. So here's our cobot, but in the background, you can see this is our high bay in the manufacturing engineering building. It's housed in our smart manufacturing demonstration center, where we have a Cisco server, and we have some Internet of Things devices from Cisco to connect this into kind of a central database, central system. And that's really what we're doing now in order to collect the data from the cobot, and also to give more information on how the user really interacts with it. So you see here we have an alternator. We have a couple cameras down here. All right, our camera human or our disassembly operators engaging with the cobot as they're doing the disassembly action. So from here, we're moving a little bit into using the cobot as a task assistant rather than the planning for how to change or how to reprogram your disassembly line, and really trying to understand how a human is going to operate or work with a cobot to do disassembly, and what are they interpreting, or what are they seeing, or how are they behaving with the cobot, so we can try to really optimize how the cobot supports disassembly. And in this system, we have 2 laptops, we have the robot, and then we're collecting facial feature information, along with all of the trajectories and information from the cobot. And these files then get combined so we can determine how your engagement or how you're interacting with the cobot really impacted how you did your disassembly, or how you programmed your disassembly, in hopes that these cobots are something that we can demonstrate that remanufacturers would find benefit in, and would hopefully help their disassembly operations, which is a place where they do want to improve. And where do we see this going? So this is from some conversations with MIRA and some meetings from MIRA. MIRA is the Motor Equipment Remanufacturers Association. They're located near Wayne State. Association of really small to medium remanufacturers who are doing disassembly. They may supply certain OEMs. There's a range. You may have very large remanufacturers that have vast collection networks for cores, have a variety of end customers, and then there's also smaller companies that deal with very specific parts. But one thing they're concerned with, or they see as something that could be improved, is the disassembly side, not just from improving the speed of disassembly, but also assisting the manual human operator doing the disassembly with how to take it apart. So recommending either fasteners, or doing some recognition of what tools they need and what order they need to disassemble it. But also at the same time making decisions on if that part's good or bad. Is that going to make them money, or is that part doesn't have enough value, the quality is too low that they really need to scrap it and recycle it, and they shouldn't really pursue remanufacturing that part. So this is where we're looking to in the future. We have AR here, and then in order to identify it's scrap or good, you have to have some sort of image recognition and analysis with some classification for the history of those parts, or some feature recognition to identify scratches, to identify gouges, to identify issues externally that you can see on the surface with the part, to help guide the decision of this needs to be sent directly to scrap. And we want to avoid doing any more subsequent processes on this component, because we're going to recycle it or scrap it anyways. So cobotic disassembly, I'm excited about it. Hopefully that came through. I think it's a very exciting area. There's a variety of researchers around the globe that are looking at this. They're studying different problems on safety, how you do task assignment, what is the human intent, how do you do it for specific parts? Does it apply to specific components or types of products or other components? So I think it's a very exciting area, and one that has a lot of potential to really help the disassembly and remanufacturing industry. All right, we have, I think I'm staying pretty pretty good on time. I think we have about 20 minutes less, 25 minutes. I want to try and bring it all together with design for disassembly. So design for disassembly is something I've known fairly conceptually. Right? I want to use similar materials. I want to use similar fasteners. But quantitatively, I've always felt that there is something missing. And what really I think is missing is how do we access a lot of what I already talked about in automation and sequence planning to help the design decision. So it's not just about rules on similar materials, rules on similar fasteners, right? But we can really bring in a lot of what we learned from disassembly sequence planning and disassembly automation into the design side. So if we look at design, why do we want to do it? One is disassembly, and this is really where I focus on. Another one is for cleaning. So how can I best clean it after disassembly? Right, that is the next step. So if you have product designs, if you have material that really support the cleaning side, it's going to make that easier on the remanufacturers. Reprocessing. All right, so this gets really more into design of specific components, not designing of your sequencing or designing of how you're going to take it apart. It's adding some material to one component so that it can be remanufactured a little bit later. You know, rotors on a car, you can usually turn them down. So that's a type of repair, remanufacturing, extending the use. So if you build that into the beginning, then potentially there's a very targeted remanufacturing piece that these companies can do at the very end. And then reassembly. So is it built for reassembly, or is once I disassemble it, it's going to be done? I'm not going to be able to reassemble it. So where we're doing work on is really the disassembly side, how you take it apart, and hopefully that sort of makes sense with what we've talked about in the first two sections here. And a lot of it is, how do I take advantage of my optimization? How do I take advantage of what I've learned from cobot disassembly, and how do I bring it back into CAD? Once I have my design, my assembly design, I want to be able to do the disassembly optimization methods, right? I want to be able to simulate what a cobotic disassembly might be. I want to be able to do all that in the design. And one of the issues we've seen so far, the best that we know of, is that one real significant piece of information is missing, and that's your disassembly precedence matrix. So all the way back at the beginning of the sequence planning method that I talked about probably about 40 minutes ago, right? This is the essential information for any of the optimization. If you have this, right, you have a pathway to doing a lot of analysis on disassembly. And what we've seen is that this is missing right now, or it's not easily retrievable from the CAD environments. You may have to do it manually. Well, if you have a very large assembly, that's very time intensive. So our work in the design side has been pushed to, how do I retrieve that information? What methods can we develop? What methods can we research so that from the CAD side, I can get my disassembly information that I need to plug into my optimization methods, my sequence planning methods. So everything that I can do in sequence planning, and there's a lot of research and a lot of methods out there, I can bring that back into design, and now I can access those. And to do that, we need to sort of think about, right, the reverse of how we're doing CAD. So we need to have a way to evaluate, what are my contact constraints in my parts? What parts are touching each other that prevent me from disassembling them? Now, what are my non-contact interferences that prevent me from disassembling a piece? So if I have a housing with a component on the inside, I can't disassemble that component on the inside because it's eventually going to hit this housing piece, right? So I need to identify those type of interferences that really control how I can disassemble this part. And then going forward, and we haven't quite hit there yet, is the non-traditional disassembly. So, you know, can I cut a hole in my piece to get to my material? How do I identify that I just want to destructively take this thing apart to get to this one high value material? And so we've been doing some work on the contact and non-contact interference, so that from the CAD side, we can start investigating and doing some analysis on what disassembly might look like. So a lot of that is taking the geometry from the CAD side, trying to pull out some of the face information for different parts, vertices, and then testing the collision. And this is where our approach has gone so far. We have a few ideas on how to take it into the future, but really we're trying to search through this CAD model and determine if I take a piece apart, if I take one component apart, what am I going to collide with? And then going back and doing that again for all the components in this assembly. Right. So in this case, I have a face here. This is one face of this rectangular component. I want to see moving out in the direction of this face, perpendicular to this face. Am I going to collide with anything? Am I touching anything right now? And if this is built into your assembly file, right, when you're doing the assembly, we might be able to get at that pretty easily, but we haven't seen that that's really built in. And we're having to go in and retrieve that information with methods that we develop on our own. So here's a case for contact and non-contact, a pretty trivial, simple case. This block and this plate are contact here. So we need to identify that for our disassembly to eventually make that precedence matrix to characterize disassembly. And know in which ways it can move away from that plate. If we assume this plate is stationary and can't move, then based on this contact relationship that I see here, this block can move up. In this case, I have a square with a square hole in it, a square piece missing, and I have a block. So in this case, I could move this block up and down, and I'm not going to have any non-contact constraint. If this piece here is a housing, kind of take a slice of a part of a housing, and this block is sitting inside of that, then I'm not going to be able to disassemble this block because I'm eventually going to hit this piece. How we have started that is we look at a single stage first. So this is sort of how we approach this problem. If we were given this very test assembly here, at this stage, I want to know what things I can disassemble and in what direction. And to do that, we can search through all these different interferences or relationships between the parts and obtain what's called an interference matrix. So we're seeing our list of parts here in the rows and our directions in the columns, and that gives us a sense of which way these parts can move or can't move. So that's the first step. And that leads to a disassembly precedence criterion diagram. So after we're looking at those different movement capabilities, we're trying to find out which ones have the most flexibility or can move or be disassembled the most, which one has the most accessibility. So that might be the first one that we really need to disassemble. So that our interference matrix gets transformed to this criterion table, and that eventually gets transformed into what we showed in the very first section, the precedence diagram or the precedence matrix that shows that these two parts can be disassembled or they cannot be disassembled. And from there, we can make some inference into which one is best or which one can most easily be disassembled. So this is a weighted liaison graph. You see larger nodes meaning that likely that piece has the most movement capability. So part 5 or part 6, they're the ones that you might more easily be able to assemble at this stage. So that's one stage, right? So at this stage, you can make a decision, I'm going to disassemble part 6. And once you do that, now you need to do it again for the next stage, right? Because once I remove a piece, I have almost a new assembly. I might have new relationships come up, or I might have relationships that don't exist anymore. And so now I need to kind of iterate and redo my process again. So what we find is if you repeat that, right, and this is for a ballpoint pen, if I do it at the very first stage, I obtain this type of network, directed network. And so as I disassemble parts and as I repeat this, I start to build my directed disassembly network. So in stage 2, right, I'm starting to find out 2 pieces that I disassemble. Stage 3, 3 parts that I disassemble, all my different options, my nodes for my disassembly here. Stage 4, all my different nodes. And stage 5 to fully disassembled. So now by repeating this sort of collision into our disassembly sequence planning methods, we can potentially put it into some of our cobotic programming methods to see how my disassembly sequence is going to perform, to find the optimal disassembly sequence, or to change our design to see how my disassembly sequence can be improved. So with that connection, we feel that you have access to a very powerful tool, and it's not just the sequence planning program I showed. Literature is rife with disassembly optimization methods for planning your disassembly line. So which station should get which tasks, planning gripper changes for disassembly for a robot, planning direction of disassembly. And so with this information, nearly all of those methods really become accessible at the design side. So for us, sequence optimization is one area we want to integrate now with it. So we want to be able to put in our solenoid valve. design. We want to be able to change our design and then demonstrate how changes in our design can really make our trade-offs better, right? How it can really improve the disassembly that we're going to have at the end of life. We want to simulate what the cobotic disassembly is going to be like, right? If I can get that precedence matrix, now I can start planning for how I really need to do the automated disassembly. Once you have that, yes, it can be disassembled. No, it can be disassembled. It's not a far jump to telling or evaluating in which direction it should be disassembled in, or which direction it has to be disassembled in. And once you start getting the direction of the disassembly, you're able to translate that into trajectory planning for cobots, right? So now at the very beginning of the design stage, hopefully I can start planning my automation processes for how I really want to disassemble this. And then another area that we've done some preliminary work on is starting to ask the question of, all right, we can do the optimization methods, we can do the programming, we feel like there's a direct connection there, but really we're still missing that piece of what happens to this component during the use phase. And what happens to that component or product during the use phase does change how it can be disassembled. And in that case, we can start to simulate different wear patterns in an assembly to see how our disassembly really is going to change, or if our disassembly opportunities or disassembly planning really needs to change at the end of when it's at a remanufacture. So in this case, on the left here, you see this large network. This is of a small assembly, and this network was generated from doing this iterative process and extracting this data from the CAD model. And this is what we assume to be perfect condition, so straight off the manufacturing line. And then we induced a couple wear patterns in certain bearings, basically saying what happens if this bearing wears out almost completely? Does our disassembly change? And initial results are showing a change in the network, right? So we're seeing a different network design, and the easiest way to see this now is just kind of based on the shape and identifying some of how the network changes. But if you dig into here, there's different relationships between the nodes. Metrics on how many connections we have between the nodes show that we see changes at certain disassembly levels, right? So now if I can integrate that sort of wear, integrate that type of degradation analysis into disassembly, now I might be able to account for that in the design. If I see a major change in how I need to disassemble this product because of a specific wear that might happen, hopefully I can account for that now in how I design that component or product. So that sort of completes the design side. This is actually my summary side. I was trying to hopefully be a little bit succinct on the summary side. But I wanted to kind of take you through the disassembly research that we're doing in the Mars lab, not the planet, manufacturing and remanufacturing, and really on disassembly. Now, the planning side, again, it really boils down to having a model for your disassembly, an objective function, and then some solution approach. And it's pretty standard, that problem formation. You'll see it all over the place in disassembly research. On the automation side is really where we want to try and take advantage of scaling up the disassembly process, so that we can access more material. In the case of critical materials, that we can get more critical materials out from the used products back into the forward manufacturing side. For other remanufacturers, so that their processes can operate a little bit more efficiently. The design side is where really everything comes together. And said, really, it's been more of a concept for me, but our hope is that with some of the work we're doing, it becomes less of a concept, and we're able to directly bring in the automation side and the planning aspects, the optimization into design, so that we can make changes in the design side that really go back to make your planning more efficient, so that it goes back so that the automation is a little bit easier or known in advance. And all of these things, so all these things, the main objective is really to help an advanced disassembly here. And there's other ways to do it. Looking at product service systems where you control the entire lifetime of the product, so you in an attempt to remove sort of that unknown between the factory and the consumer, right? But everything we're doing is really focused on disassembly, because we feel that by attacking disassembly, by really focusing on disassembly, it's one of the first stages, one of the first operations that happen at a remanufacturing facility or a recovery facility. And if we can improve that, that one operation, we can make all the other operations there a little bit more consistent or a little bit more efficient. If we can really target and we can really advance this first disassembly operation. And then with the design methods, if we can really show the benefit of those and show that we're able to use all these nice optimization methods back in design, that we can really make that disassembly decision at the very start, so that that circular economy really is something that's planned in for at the beginning, and isn't something that at the end a company says, well, okay, we have demand for these parts, we got to figure out a way to disassemble and remanufacture them now. But it's already known. There's a lot of other factors that go into that, kind of with policy in place and what manufacturers might be responsible for or not responsible for. So we know that there's a lot of other factors in there, but hopefully our research can help contribute to it a little bit. So thank you. I want to appreciate Wei Song and Wayne State for giving me the opportunity to do the presentation. I want to acknowledge the PhD students, master students in the Mars lab, Dr. Kyung Yoon's lab for we're collaborating on the engagement study, Oak Ridge National Lab, when we were working with them to do the scale up, and then MIRA, the Motor Equipment Remanufacturers Association. We learned a lot from just listening to the remanufacturers there. So I think maybe a couple minutes early, and we have plenty of time for questions, discussion. I don't know the best way how you want to operate the questions, Wei Song, if it's easier chat or just unmute. I'm happy to stick around for as long as it takes and talk about disassembly for, well, I would say for the whole day, but I have some other Zoom meetings, so.
Okay, thank you, Jeremy. You are open to questions right now, right?
Yes, yes, please feel free.
Okay, so we actually live quite a good chunk of time, you know, because normally when you go to a class, after the classroom, your instructor go to next class, you know, immediately. So there's not too much, you know, of time and opportunity to ask questions. Here we would like, if you have any questions, Kirsten, I think they can unmute themselves. Can they?
That is correct.
Yeah, if you have any questions, you can unmute yourself, and then maybe it's good to introduce your, you know, who you are, where you coming from, and then start asking questions. Okay.
You can also put questions in the chat if you are more comfortable with that.
Okay.
This is Nancy Philippart. Jeremy, great presentation, very interesting work. I guess the question that I have for you, I mean, first of all, you know, I love the total system approach that you're taking here. And I certainly appreciate, you know, the power of, you know, being able to design for disassembly up front. I'm interested if you have gotten any energy around that. And the reason that I'm saying that is, in my experience in the automobile industry, we struggle to get design for service requirements even comprehended. And even today, I'm not sure that the industry does that well. And this kind of takes it one step further. What do you think will need to happen in order for, you know, design for disassembly? I mean, do you think it's going to take, in the US, doing what Europe has done to say, tell the manufacturer, you own this thing at end of life, therefore they have incentive? Or what's some of your thoughts on that?
Yeah, no, a really great question. And I think it brings up a couple of really interesting points. So I think the first one is comment on the automotive and the different product markets is a huge decision when looking at disassembly. So it's really critical if you're evaluating disassembly or if you're talking about disassembly to understand what sort of market or what sector you're in. So something like heavy equipment, Caterpillar, they have that built into their system because the parts are so valuable and they've invested so much into them. The automotive side and some of the aerospace side, I think, is like that too from some of the brief conversations I've had. Automotive side is really interesting. I think so 3 or 4 years ago, we had a guest speaker from maybe GM at one of the automotive companies on the sustainability side. And so we were asked them about sort of this planning and the recovery and the remanufacturing. And I don't know if it's good or bad, but the US anyways, we have such a, I guess, flourishing or lucrative sort of secondary market for automobiles in terms of parts scrapyard that it sort of takes care of itself a bit. Because there's such demand, and because it sort of takes care of itself, there's not really an incentive to design it in at the beginning, because there's these independent core collectors that know that there's value in those parts, and they know where to sell them, and so there doesn't, it's sort of formed because of the value in the parts without one of the manufacturers really starting it or being responsible for it. Now, there is communication happening. So like with Mira, they're under MEMA, Motor Equipment Manufacturers Association. So there are these conversations of from remanufacturers. Well, hey, if it was like this, we could really disassemble it easier. We could really remanufacture it better. But the communication that doesn't come through. There isn't that type of power maybe from the remanufacturers to influence the design side that way. So I think you look at a couple of things. One, it could be a policy kind of issue. But I think if we look out, if it's a policy that you have to be responsible for the car, the manufacturer has to be responsible for the car, has to know what happens to it at the end of life. Really, it's going to be the same people doing it. You just might have another piece of paperwork to say that car, we disassembled that car, we took back that car. Really, it'd have to be sort of a change in maybe the vehicle. So with the electric vehicles, now we might see this start to shift because of the battery technology and because of the value there that the automotive companies and what they've seen from the remanufacturers now, that's going to be a high priority to make sure that that's accessible for them and they get that back because of the change in the material and the change in the technology there.
Great, thanks.
Some thoughts, no answer, but hopefully some interesting thoughts on it.
Yeah, no, good perspective. I hadn't, I think your point about the electric vehicles and the, people will do kind of what's inherently in their economic interest oftentimes. And with electric vehicles, oftentimes, you will see that there might be more value, therefore more incentive.
Yeah, and disassembly of battery packs is an area that's currently pretty active in disassembly research. So what's the best way to disassemble to get to those battery packs and to get to that material?
Great, thanks. But wonderful presentation.
Thank you, Nancy. I think we have one in chat.
Right. Yeah, you get a question from
Mark in chat. Is there an inherent conflict between design for disassembly and design for application? I think it's an interesting question. I think it's a very good question. And I think there can be. You may have some areas where it's win-win, but I think there will be some trade-offs, or there's for sure going to be some scenarios where you have a trade-off between, if we change our design this way for disassembly, we will benefit here, but it is going to hurt us maybe in the application side. So I think with some of the optimization methods for disassembly, if we can bring that in and then incorporate the application side, hopefully we can kind of make those trade-offs transparent, and so that then you can decide, okay, is it okay for me? Would I sacrifice that design for application to have this easier access at the disassembly side? I think there's a lot of interesting things we can do to show that. And to allow then the designer to make that decision. Maybe you don't sacrifice the application at all, and that's okay. You just have to kind of deal with the disassembly side then. Hopefully, I think it's a really good discussion, question mark. I don't have a great case study on it, but I think it's a really fascinating question.
Yeah, I worked in as a tier 1 making shock absorbers for many years, and you'd have to have the OEs get on board to say, okay, we're going to allow you to do this. It's like lightweighting. We're going to allow you to do this. We'll give it up a little bit of performance or application for the disassembly with IMDS and end of vehicle life type things that are going on in the industry now. So, okay. Thank you. Very, very good presentation, Jeremy.
Thank you, Mark. Appreciate the question.
Okay. Jeremy, very nice presentation. As you know, since this is about the disassembly and then about sustainability, I want to take this opportunity to you know, share with the audience that College of Engineering have several programs, you know, that are related to the sustainability, including, you know, sustainability engineering was in you know, chemical engineering, and also the environmental and sustainability engineering is a new Master of Science program which has started last year. And also, Jeremy, do you want to say a few words about that? What other research activities and the programs in the ISE?
Yeah, I would love to. I'd love to have that opportunity. So in the ISE department, Industrial Engineering, Industrial Systems Engineering department, we have a wide array of fascinating research happening, both with industry and at the fundamental level. So we have the research that I talked about here, disassembly. We're also doing some research with digital manufacturing and making processes more efficient. And then if you expand that out, we have faculty doing research on the really design theory side, which is very interesting, especially from some of the topics I talked about here. We have faculty that are really studying drones and drone control mechanisms. And I'm going to pick on Yan Chao because I see his name here. And thank you for attending, Yan Chao. He's doing some fascinating work with drones, has a career award from NSF to really kind of demonstrate the importance and the impact of that research. We have other faculty that are doing research in virtual reality and really looking at the human intent that I mentioned, and understanding and predicting how a human is going to interact with a robot. Faculty doing research in power systems for windmills to really make those more efficient, and then automated guided vehicles in manufacturing. So we hit on a lot of areas of manufacturing, energy generation, healthcare systems, and then data science and analytics. So that's some of the research that's going on, but some of our master's and PhD programs are just equally as fascinating. We have our master's in data science and business analytics with computer science and the business school. That's very popular, that's hands-on, that's industry project focused for a practicum at the end, so that you're really working with data from industry. We have masters in industrial engineering, masters in manufacturing engineering, and masters in engineering management. Variety of programs that really help students get kind of take off and have a springboard into their careers in industry or academia. We collaborate a lot with industry. So a lot of the researchers that I mentioned, they're doing a lot of really good work with specific industries, automotive, power generation. We have two entities that really help that out. One is the Smart Manufacturing Demonstration Center. That's a partnership directly with Cisco. And we're working with them to develop some demonstration on their technology, along with the cobot experience in the high bay. And then Industry X, Center for Operational Excellence, which really has a lot of connections with how to improve operations in a manufacturing center, leveraging data analytics and data science. They have a large network, really a lot of strong industry support there for both centers. And you can find them on LinkedIn. You can find us on the website. So it's a very active department. We're doing a lot of really fun, a lot of interesting research. You know, I only have a few minutes to talk about it, but we could spend a long time touring the building when we can get in there easily, and kind of showing off some of the labs and a lot of the real good research that we're doing in the IC department. All
right, great, thank you. I just noticed our Dean Functional Futui is also on the list. He has some other meetings. He couldn't join us at the beginning to give opening remarks. I will like take this opportunity to invite him to share some of his vision about this program seminar series. Farshad, are you still here?
I'm right here. Here. Isang, thank you for the invitation, and Jeremy, thank you for your excellent presentation and also a good description of what's going on in your Department of Industrial and Systems Engineering, which is really exciting program altogether. As Wee-Song mentioned, that we do have sustainability kind of embedded into most of our programs across the entire college. In particular, the new degree program we launched, the master degree program, in environmental and sustainable engineering in the Department of Civil and Environmental Engineering here at the Wayne State. We started this seminar series. This is the first of several talks that will be happening every Friday going forward all the way up to the almost end of summer. And it is really to engage our alumni, to engage our industry partners, and more importantly, to engage with our university partners globally to learn from us what is going on in our college, what is going on in some of our research areas, because a lot of our university partners globally, they want to engage with us in research. So this way is one way of engaging them and their faculty with the work that we are doing. I feel this is a good way of connecting with the industry as well as alumni. We have some new exciting degree program we just launched, including, again, as I mentioned, environmental and sustainable engineering. Mobility is one that was launched a few years ago. Data science and business analytics in collaboration with computer science and also business school, launched again in 2019. And we have also currently launching a program in robotics that has branches in computer science, electrical engineering, and engineering technology. So we have launched recently some new degree programs that I encourage those of you who are interested in pursuing advanced degrees to please look into those on our website as well too. And again, we are hoping that in the fall, upcoming fall semester, we will be face-to-face, and we welcome our international students back to campus coming this fall. With that, I'll pass this microphone back to Wee-Song. And thank you for the opportunity to say hello, and thanks everyone for participating.
Thank you, Farshad.
What is the next talk?
Yeah, I just want to announce that in next week, Friday, we will have Dr. Steve Ramirez from Civil and Environmental Engineering talking about the smart transportation infrastructure, the past, present, and the future. That is feeding related to the mobility and the transportation research. Yeah, it will be the same time.
I wanted to also make another comment. Thank you. One thing I want to mention, I forgot to mention, I see Dr. Nancy Philippart here also on the call. So these talks are under the umbrella of the Global Engineering Education Center, which was established by a fund from Dr. Nancy Philippart in the College of Engineering. And we are definitely engaging in not only these talks to reach out to our global partners, but also I will encourage Dr. Philippart to say a few words about her work in collaborative teaching that she has done with the school in Germany, and the planning to do that in the fall with the school in Netherlands, as well as in UAE, United Arab Emirates. Nancy, do you want to say a few words about the type of work that you're doing in collaborative teaching with these two universities?
Yeah, thanks, Farshad. So one of, I know the things that I'm very passionate about is trying to provide opportunities for all of our engineering students to have what I call an authentic cross-cultural experience. And, we have some students that will do study abroad, but not the majority of our students. And we do have some students that will do global internships, but again, not the majority of our students. And so we have realized that because of the way the world works today, many of our students, regardless of where in the world they work, will be put on cross-cultural virtual teams to work globally on, whatever project that they're working on. And they may never get a chance to meet face-to-face with the people around the world they're working with, but yet they'll be expected to work collaboratively and effectively and, achieve the goals that team has. And so we can simulate that in the classroom. And so we are doing more of these cross-cultural collaborations this semester as we speak. I am teaching a course with some Wayne State students that are working on a joint project, interestingly enough, in the area of sustainability and innovation. But the real purpose of this course is to give our students the opportunity to work on a semester-long project cross-culturally and virtually with students in Germany. And as Farshad said, the university has been very active in helping faculty who are interested in this develop partnerships. So in the fall, we are going to be adding more universities to a course on technology management. And this provides our students, real good opportunity to learn from others, but also to further develop their cultural intelligence and their cross-cultural skills while actually executing, good hands-on engineering projects. So very, very excited, and certainly looking to develop more partnerships, looking for more faculty to be involved in that kind of teaching. And, certainly any alum that have ideas or ways to support that, we'd love to engage you. So thanks, Farshad.
Thank you, Nancy.
Right. Is there any other questions from the audience regarding this particular topic? Okay. Seems like we don't have.
No, I'm not seeing any in chat either.
Right.
As I say, my email is on the title page of the presentation, and I'm happy to discuss more. There's a lot more to talk about in each area. So if anybody's interested, reach out to me by email on LinkedIn or on Zoom chat, and happy to touch base later.
Sure. Okay. So if there's no further questions, then we are, then next, we will be ending today's talk. And then next week we will have, as I mentioned, just now, we will have a talk on the smarter, transportation infrastructure. And okay, we'll be on the same time. Okay, yeah, those are most of them. They're just thank you for the nice presentation. All right, so I think that we will conclude today's talk. First, thank you for all the audience, and I'm sure that from globally, some of you probably wake up very earlier. Some of you wake up, you stay very late. Thank you for attending this, and then also, thanks for Jeremy for giving this talk. And it's very helpful. Even for me, it's kind of opening to know that the disassembly, it's very important, right? For the remanufacturing. Now I know what Mars means. Next time you should starting with a Mars. Tell the people what.
That's it.
Mars.
When I made up that acronym, we weren't talking about going back to Mars. So.
Right. Yeah.
Don't worry about it.
Right. Okay. Well, thank you all. So we will end today's talk, and yeah, bye.
Thanks, Wei Song. Thank you, everyone.
Sure. Bye-bye.
Hey, Wei Song, Kirsten, did you need my presentation file or anything?
Oh, that would be great.
Okay.
Kirsten have some emergency. She left, but I think yeah, if you are willing to share, well, perfect. What we plan to do is we put in this video there, and then that we can, if the slides, you make a PDF version, so that we can attach that there. That would be great.
Okay, I will make a PDF version and I'll share it with Kirsten.
Yeah, yeah.
And if there's anything else you need, just let me know.
Sure, sure. Okay. Thank you.
Take care. Have a good weekend.
Yeah. Bye.